Is there something quantum happening underneath? Today, we're doing a deep dive into two ideas that honestly feel worlds apart. We've got string theory, this huge concept, maybe a theory of everything, and then the de Broglie waves of, well, everyday things, these tiny, tiny wave properties. So the big question is, how can these connect?
A grand theory and the subtle waves of a baseball. Our mission today is to sort of pull out the core ideas, see how they link up, even if we can't actually, see these waves in action day to day. Right, let's start with something foundational in quantum mechanics, wave-particle duality. It's this kind of mind-bending idea that everything, tiny photons, huge planets, everything can act like a particle and like a wave. And the person who first put math to this was Louis de Broglie, way back in 1924.
That's right. De Broglie's idea was, well, really out there for its time. He basically said any particle that has momentum also has a wavelength associated with it. And the formula is actually quite elegant. It's lambda equals h divided by p. So lambda, that's the de Broglie wavelength we're talking about. And p is just the momentum, mass times velocity, how much oomph it has. Then there's h, that's Planck's constant, and it is incredibly small, about 6.626 times 10 to the minus 34 joule seconds. It's like the universe's setting for how wavy things get.
And we definitely see this play out with tiny things, right, like electrons. Because their mass is so small, their momentum isn't huge, relatively speaking. So their de Broglie wavelength is actually significant enough that we can observe wave-like stuff happening. Things like diffraction patterns, interference, the kind of things you expect from waves. This is really core to understanding the quantum world. It's not just math. We see it in labs.
Exactly. But okay, now let's shift gears. Let's zoom way out. What about the stuff we interact with? Baseballs, cars even, like a speck of dust, macroscopic things. Well, their mass compared to an electron is just immense, colossal. So their momentum, P equals mv, it becomes enormous. And what happens to the wavelength then with that huge momentum P on the bottom of HP? It shrinks dramatically. It becomes vanishingly small. Let me give you a number. A 1 kilogram object moving at just 1 meter per second. Pretty slow. Its de Broglie wavelength is something like 10 to the power of minus 34 meters. That's the decimal point. Then 33 zeros, then a digit. It's so small we couldn't possibly measure it. It has basically zero effect on how that object moves in our world. Your car isn't going to diffract around a lamppost,
Okay, so we have this definite wave nature for tiny particles. It's measurable, it's real. But for big things, it's still there, according to the math. But it's so small, it's effectively gone. Doesn't matter. It almost feels, well, disconnected, like two different sets of rules. And that's where string theory kind of enters the chat, right? Offering maybe a deeper explanation.
Precisely. String theory is, as you said, a candidate for a theory of everything. And its basic idea is pretty radical. It says the most fundamental things in the universe aren't tiny points like we usually imagine particles. No, they're actually one-dimensional, vibrating. Well, strings, like microscopic guitar strings, sort of. And the really neat part is how these strings explain all the different particles we see. It's all about how they vibrate. Different vibrational modes, different notes, if you like, correspond to different particles. An electron is one vibration, a quark is another, a photon yet another, each with its specific mass, charge, all its properties. So connecting back to de Broglie, from a string theory perspective, that wave-like property isn't just some abstract add-on. It's actually a result of the string itself vibrating. That's the source of the waviness. And the particle-like behavior, that comes from how the whole string interacts as one unit. So string theory doesn't just allow for wave-particle duality. It inherently is wave-particle duality. The waviness comes from the string's vibration.
Wow, okay. That makes sense for the tiny particles linking their waviness to the string vibration. But then the big question comes back. How does this super microscopic world of vibrating strings scale up? How does it connect to the, solid classical world we see, to the baseball?
Well, think about what a macroscopic object actually is. A baseball, planet, whatever. It's made of a truly staggering number of fundamental particles, isn't it? Electrons, protons, neutrons, which are themselves made of quarks. And in string theory, every single one of those fundamental particles is a string vibrating in a particular way. So you can picture a macroscopic object as this huge, complex collection, an enormous ensemble of countless strings all vibrating together. Its classical properties, where it is, how fast it's going, its momentum, even its de Broglie wavelength. These aren't properties of one string. They're the emergent collective behavior of this astronomical number of strings acting in concert.
So wait, are you saying string theory changes how we calculate the de Broglie wavelength for the baseball? Or is it still the same old lambda equals h over p?
No, that's the elegant part. It's still calculated exactly the same way. Lambda, hp. The p is just the total momentum of the entire object, all those strings acting together.
Right.
And the object's mass. That comes from the total energy of all its vibrating strings, connected through EMC squared. So here's the key takeaway. Because that total momentum p for a macroscopic object is so incredibly large, string theory completely agrees with standard quantum mechanics. It confirms that the de Broglie wavelength for macroscopic objects is absurdly, immeasurably small, practically irrelevant. It doesn't suddenly predict your car should have a big, noticeable wavelength, which is good, right? Driving would be interesting otherwise.
Yeah, probably chaotic. Okay, so if string theory basically arrives at the same answer for macroscopic objects, tiny wavelength, no observable effect, what's the point? What's the value it adds here if it doesn't change the outcome we already knew?
But that's where the perspective shift is really interesting. The value isn't in changing the number for the baseball's wavelength. It's about providing a potential unified explanation for why that wavelength exists at all, even if it's tiny. It suggests a deeper, more fundamental reason rooted in the basic constituents of everything. It's like finding out that the same DNA code runs through a mouse and an elephant. The scale is different, but the underlying principle is the same. It suggests that the exact same fundamental rules these vibrating strings are responsible for the weird quantum jumps of an electron and the predictable arc of a thrown baseball. It's about seeking one framework, one set of rules for the whole universe, from the tiniest scales to the largest. That's the real ambition here.
So that incredibly faint, theoretical, wave-like nature of the baseball, it's like a tiny echo, a residual hint of the quantum dance happening with all those strings deep inside it.
That's a great way to put it, an echo.
Even though you can't see the baseball diffract, the fact that we can assign it a wavelength, even a ridiculously small one, it reminds us that the classical world isn't separate from the quantum. It's built on it.
Exactly. And string theory, while still a theory and needing experimental proof, of course, it offers a possible picture of what that quantum foundation might actually be, made of strings. So the value isn't a new prediction for baseballs, it's the conceptual elegance, the potential unification. That's the goal.
Right. So wrapping up this deep dive then, we started with strings and baseball waves, seemingly miles apart. But we found a potential bridge. String theory suggests that the solid, predictable world we experience emerges from this incredibly strange, probabilistic quantum world underneath, a world perhaps made, fundamentally, of tiny vibrating strings. It leaves you with something to think about, doesn't it? Next time you pick something up, something solid and real, consider that, according to this idea, it's this vast orchestra of vibrating strings silently performing a quantum dance that gives it an almost imperceptible wavelength. Makes you wonder, what other hidden quantum realities might be underpinning everything around us, just waiting to be understood?